Okay, so I'm Nathan Hara. I'm a postdoc at the University of Geneva, and I'm going to talk about detection criteria. But first, a little bit of advertising. So with Eric Ford, we wrote a review of statistical methods for RV detection, which is in two parts. You have the main text, which is really where we tried to make clear what are the questions that we are trying to answer and what is the general flow of the analysis and what are the specific choices, like what kernels are we using, what priors are we using, and so on, is in the supplemental appendix. And if you think, so there is a public version on the annual review website, but the archive version is still to be done. If you think there are some references missing, you can write to us, so we can maybe add them to the archive version. Okay, so optimal and robust exoplanet detection. Let's first talk about optimal in that title. So what is the detection criterion? In fact, it's something where you set in input an RV time series, maybe indicators. You have a noise model, so a likelihood function, possibly priors, and it outputs a number. You compare it to a threshold and you say, well, I have detected an additional planet. And so you compare 1 versus 0, 2 versus 1, 3 versus 2, and so on. You can do that with a periodogram plus a false alarm probability or with a base factor. These are the most common options. So let's try to compare them. I made a simulation where I simulated 1,000 RV data sets in which I have random planets, 0, 1, or 2. And I'm going to analyze these systems with the periodogram, with the L1 periodogram, with the base factor, with many different methods. And as I move my detection threshold, I will have more or less false detection. So you see here, as I move towards the right, I become more and more stringent. So I have less and less false detections and more missed detections. So now if I want to compare the different methods, what I will do is to plot the total mistakes, so missed planets and false detections, as a function of the number of false detections. So for this particular level, I will have a certain number of both. Then if I increase my threshold, I will have less false detections, and so on. So, okay, base factor and FABs and other stuff. Can we do better? Could we have a curve which is lower than the best candidate so far, which is the base factor plus the posterior distribution of variance? These they do not encode where the planet is, the FAB nor the base factor. It does not tell you where the planet is, and they are not defined on an intuitive scale. You would say that you have a planet detection if the base factor is greater than 150, but it doesn't really mean anything. So if we were to try to think of an optimal detection criterion, what would it look like? So let's first define what a detection is. Detection is, I have a system, I'm saying, well, there are this many planets, and this is where they are. For example, if I'm claiming that there are 2 planets on this particular, around this particular star, and I'm saying, well, there is one planet with this frequency in this range, and one planet with a frequency in this range. That's what I claim. Now, maybe, in fact, there are 3 planets. One, I say there is a planet here, and there is one, so I have one true detection. But I say that there is in the other frequency box, and there is one. So I have one false detection, and I have 2 missed detections. Okay, so that's what I call a detection. And in fact, the formalism works if it's not frequency box, but it's, for example, frequency and mass. And I'm saying, well, I detect a Jupiter in this frequency range. Now, a detection criterion is a function. It's taking in input a data set, and it's saying, well, for this particular system, you have 2 planets, or 1 planet, or 0 planet, or 3 planets, and this is where they are. And when I'm talking about an optimal one, this is really what I was talking about at the beginning. It's for a certain tolerance to false detections. I want to minimize the missed detections. I want as many true detections as possible while being sure that I'm not allowing too many false ones. We have a formal optimization problem, and a formal optimization problem has a mathematical solution, blah, blah, blah. And then what's the optimal solution? In fact, it's very simple. It's just a simple post-processing of what you already have when you compute Bayesian evidences. So you take your frequency box and you slide it across the frequency range, and in each box you're asking, what is the probability that I have a planet there? So that's what you compute. And then you say, well, I'm taking a fixed threshold. Everything which has a probability to have a planet there greater than, for example, 99%, I'm saying, okay, this is a planet. So if you want all the details of how you can compute this, in particular in this reference, there is a link to a notebook, and you'll see it's fairly easy once you know how to compute the evidence and the posterior probability, which is the hard part. And it's been used, for example, in the detection of the first circumbinary planet detected with. Okay, so how does it perform? We did all this work, all this math, for what? For this. So this is the performance of the new criterion. So for a low tolerance to false detections, on this particular simulation, you have 30% more true detections. And in terms of interpretation, the true inclusion probability, the probability that you have a planet, this is a true posterior probability. So if you have a bunch of detections, they all have a 99% probability to be right. Well, in fact, 99% of them are right. If you have a bunch of detections which are 90% sure, 9 out of them should be right. You don't know which one exactly, obviously, because that's what statistics do, but at least you have an interpretable threshold. So the base factor and FAP, they were not optimal. Now we have the optimal one. They did not encode where the planet is. Now the new criterion hard codes it, and it's defined on an intuitive scale. So we should think it's perfect, but obviously it depends on whether your model is right. Because if your model is not right, then the criterion is meaningless, right? So that's where we move from optimal to robust exoplanet detection. And we want to estimate whether a detection is robust. So you can do evidence model comparison, trying to compare many different models of stellar activity, and this is fine. But if all the models that you compare are really bad, the fact that there is one better than the other doesn't mean that it's not really bad. So you want to compare your model with the data in an absolute sense, and this was the object of the talk by Sarah Blunt. It's like, it's not comparing stuff with one another. Am I correct? Am I correct in an absolute sense? And so what you can do is you have your data, you know that you're going to take data later, and you're going to predict what you should have. So if I understood my data, if my model is correct, when I predict what I'm going to predict what I should have in future measurements, then you have the actual data that you took and you compare the two. How you do that exactly, and so there is a framework that I propose in this reference, and there is a nice thing called the data processing inequality, which tells you in principle the maximum amount of information that you can use in the predictive distribution. So you know in some sense that you can't do better. There is another way to look at that, which is to say, well, actually, I'm not really sure about my model, but what I want to know is my signal stable in frequency, phase, and amplitude? So if you want to disentangle the two, also there have been some methods proposed by Phil Gregory, and in another paper that I wrote with Jean-Baptiste Delille, Nicolas Unger, and Xavier Musc. And also, if you want it to see combined with another idea, which is the L1 parallelogram, you can go check the poster by Jack Lubin, which is very nice. Okay, so that's about, so everything I said has nothing to do with any physical input. It just has to do with once I have the likelihood function defined. But now I can ask, well, okay, but I can try to make my models better. So the existing models, for example, for stellar activity, they are based on qualitative arguments, most of them, at least. So for example, the quasi-periodic kernel, the stochastic harmonic oscillator. And what we did with Jean-Baptiste Delille is to say, well, actually, let's take a look at the star, have a physical model of what's going on, and then we derive the properties of the kernel, of the GP, from the star. So now we have a GP with hyperparameters, but the hyperparameters are stellar parameters. And something which kind of amazes me is that just with the RV and with the photometry, we were able to constrain the inclination of the sun. So now, theoretically speaking, we still need to figure out how reliable that is. But in principle, we could do something like statistical Doppler imaging, where you don't have the resolution to know exactly what the surface of the star is at a given time, but you have the statistical properties of the spots on the star. So we also discuss why we have phase shifts between RV and indicators, how to build indicators, and also that we are losing information by assuming that the stellar processes are Gaussian. So stay tuned, it's going to be on the archive soon. And yeah, something to mention is it's kind of in the same spirit as some earlier work by Rodrigo Luger, which Megan is going to talk about, I guess, but from a completely different perspective. Okay. So in conclusion, the idea was to try to have an optimal detection criterion. So now there is, with simple post-processing, so you don't need fancy new numerical method. You just need to reanalyze the output of evidence calculation. You have a mathematically, demonstrably optimal detection criterion. Also, optimality, in that case, it's meaningful only if the model is correct. And I guess it would be very nice, as Sarah was making the point, to explore the cross-validation option and to try to validate the model in an absolute sense. And also we have some new stellar variability model. And again, if you want to take a look at the review and say, well, actually you forgot our paper or this paper, which is really interesting, please feel free to reach out to us. Thank you.
Thank you, Nathan. Are there any questions?
Thanks for that interesting talk. I wonder if you could say about the first part of your talk, what noise properties are assumed in the data? For example, if there's systematics that have time correlations.
In the simulation or in the theory?
In the, well, so in the optimal, yeah. So these sort of plots, what sort of?
So this particular plot is for a simulation where you have both white and correlated noise. But like the theory is valid once you've defined your likelihood model. It's not dependent on any kind of assumption. But for this particular simulation, it's red noise with exponential kernel and white noise.
Great. Any other questions?